In this presentation, I will introduce our work, namely enhancing code vulnerability detection via vulnerability preserving data augmentation. And this work was collaborated with researchers from NTU and SMU. The graph neural networks has been widely used in detecting software vulnerabilities, and the main of the ideas of such works is using the graph neural networks to learn the code semantics for the vulnerability detection. And through our broad literature review, we observed those most existing work ignore the specific types of vulnerabilities. They usually mix all different they usually mix vulnerabilities from different types, such as CWE, for example, the buffer overflow and memory leak together to train the classifier. But the problem is, the reality is that the different types of the vulnerabilities usually have different types of characteristics. So it raised a question: can we train the classifier for each type of vulnerabilities? So by reviewing the existing CVE report, we observed the different types of vulnerabilities are extremely unbalanced. For example, there are more than 20K CVEs under the category of memory corruption, but there are only around 900 for the file inclusion. So to address this type of issue, we proposed the FG welded consisting of 3 sequential parts. The first part is the data collection, and the second is the vulnerability preserving data augmentation, and the third part is the edge-aware GGNN construction. To collect the data set, we firstly gather the commit related to the vulnerabilities, and then extract the vulnerable and non-vulnerable functions from the commit. And for the vulnerability-related commit collection, we firstly define a list of keywords and use them to filter out our targeted vulnerable functions. So in all, we have collected 5 types of CWE data, vulnerability data, including CWE 404, 835.120, 672, and 362. And for each type of CWEs, there are several keywords to help us to retrieve the vulnerability-related commits through the message matching. And as I introduced, it is quite difficult to ensure that each type have a sufficient number for the learning phase. So we propose a data augmentation technology to scale up the collected data, and also keeping the semantics remaining unchanged. And this vulnerability preserving algorithm consists of 2 steps. The first step is that after slicing the original function to get the vulnerability-related statement, we conduct the forward slicing on the program dependence graph to find the future dependent statement. And afterward, we further conduct the backward slicing to find all the related statements. And these related statements are defined as the vulnerability-related statement. And through the slicing algorithm, we can obtain a list of vulnerability-related statements, and then we define 5 types of mutation operators to augment the data based on the vulnerability-related statement and the vulnerability-unrelated statement. And the add mutation aims to rename the identifier in an assignment statement and add them back to the function. And the AI mutation aims to add an if condition, which is logically true, always logically true before the assignment statement where this assignment is vulnerability unrelated. And the RO aims to reorder the assignment statement. And for the delete mutation, it aims to delete the statements that are not related to the vulnerability. And for the RN mutation, it aims to rename the identifiers. And based on the mutation, we further proposed an edge-aware GGN for training the model. And this method incorporates the edge type information for GNN, which could further enrich the capability of the detector. And we use the edge type to encode the edge information and then combine both the node embedding and the edge type embedding for the message passing during the learning phase. And finally, a classification layer is used to make the final prediction. And during the training stage, we train a binary classifier to detect each type of vulnerabilities. And at the test time, we used each classifier to make a subsequent prediction, and the final prediction is then determined by a majority voting. The data set is shown in the table on the right upper corner, and we compare our approach with 7 baselines, including the static analysis to Valdim MVP and the deep learning-based approaches like multi-head attention, Divine, and Coldbird. And firstly, we compare our approach with the baseline method. We can find the Valdim has less false positive samples, and it is quite reasonable because Valdim relies on the expert crafted features, and the recall value is lower than our approach. And this indicates the Valdim has more false negative samples, as these handcrafted features can only cover a very limited number of vulnerabilities. And the MVP have better performance than Valdim, but also lower than ours. And while comparing with the deep learning-based approaches, we find the Coldbird usually has a better performance than other baselines, and it is because it is a pre-trained model utilizing a huge and massive amount of data for in the pre-training phase. However, the performance of Coldbird is still lower than ours. And we further conduct an ablation study to evaluate the effectiveness of the proposed mutation operators. We can find, in general, incorporating these 5 types of mutation operators can significantly improve the recall and F1 scores. And those different types of mutations exhibit inconsistent performance compared to the original model. And lastly, we conduct the experiment to compare our edge-aware GGN with some traditional GN, such as the GGN and GCN, to make a fair comparison. We only compare the result of different GN variants with the FG Valdat now. And we can find the edge-aware GN, which encoded the edge type information, reduced the difficulty for the model to detect the vulnerabilities. And in conclusion, we introduced a fine-grained vulnerability detection, namely FG Valdat, and proposed a novel vulnerability preserving data augmentation technology. And furthermore, we extend the GGN to an edge-aware variant to capture the edge information for the GN learning phase in the task of vulnerability detection. So, any questions? You mean program analysis based?
Yeah, exactly.
Not yet. Not.
See the tables, the recall might be high, but the precision is not very perfect, as I say. So have you considered to maybe combine or just compare with them?
We didn't done it yet because the motivation of this work is try to figure out how whether we can use a more specific vulnerability type as the detection, the target of detection, and then using the a voting mechanism to reach a better performance. So basically, the methodology of the program analysis-based vulnerability detection is totally different from the learning-based approaches. So we didn't include that type of approach as our baselines.
Okay, any other questions? Yes.
You said you were have a preservation of the vulnerability. So do you provide any guarantee of this?
That is a good question. Actually, if you check out the defined mutators, the mutation operators, you can find the semantics of these partial code remains unchanged. So that is a remaining the semantics unchanged, preserve the semantics unchanged is the basic rule. The basic rule. So, which means we won't propose do any mutation that could change the mutation. Change the semantics. Thank you.